get this pointer going. Okay, good. So we're going to talk about statistical mechanics. And first, we're going to do a bit of an overview, and then we will talk about ensembles, averaging. We will talk about examples from physics and chemistry, for example, how to calculate the properties of monatomic ideal gases, diatomics, polyatomics, adsorbates on catalytic surfaces, etc. And in the end, we're going to talk about kinetic Monte Carlo, which is a more advanced application of statistical mechanics. And it's actually a large part of my research is on kinetic Monte Carlo. So we will review some of the methodological aspects there. Now, in the course, so far, you have studied small entities like electrons, atoms, and molecules. So this picture here shows water, ice. And the question is, how do we link all of these phenomena that you have already seen with the macroscopic world? Right, so with the methods that you have discussed for electronic structure, for instance, you know how to calculate the wave functions and electron densities for these things here. And then you know that by the Born-Oppenheimer approximation, you can have some models for the interparticle interactions at the microscopic world. So, of course, we cannot really see molecules with the naked eye anyway. What we feel and touch is matter at the macroscopic level, right? So this is our ice cube. And the question is, how do we link, right? How do we link the scales? How do we go from here to there? And this is a non-trivial problem because we're talking about several orders of magnitude, right? Going from the microscopic world to the macroscopic. So we're going to start with a refresher in thermodynamics, classical thermodynamics. And then we're going to talk about the statistical mechanics framework. So we will review concepts like microstates, Hamiltonian, averaging approaches. And finally, we're going to talk about ensembles, specifically 3 of them, which are quite popular, or probably the most popular ones. Of course, these are not the only ones. There are others that you may encounter in your research. But if you know how to think within this framework of statistical mechanics, then the rest is really technicalities, working out for different ensembles, what are the partition functions and the equations, etc. So let's start with the thermodynamics memorandum. These should be known to you, these concepts. So I'm going to go a bit quickly here. But if you have any specific questions, we can discuss. Okay, so if we consider a thermodynamic system like this, this ice cube, which is not just an ice cube in a box, it's ice cube in equilibrium with water liquid in equilibrium with water vapor, right? So I'm looking at this at the triple point. The conditions are shown here. So the macroscopic variables that we can measure in that system include temperature, pressure, and the chemical potential of the water molecules. And we would like to, so in addition to these variables, right, which are intensive variables, we have extensive variables. So we're talking about the number of moles or molecules, the volume of the system, and the entropy. And the idea is to find equations that relate these intensive and extensive variables with thermodynamic potentials like internal thermal energy, the enthalpy of the system, Helmholtz free energy, and Gibbs free energy. So you might remember that intensive variables are variables that don't change, right? If we change the size of the system. So if you think about this as a box, right? A box with these 3 water phases. If you double the system, put the 2 systems together, and then remove any partitioning that you may have, then the temperature of the final system is going to be the same as the initial system, right? Which was half the size of the final system. whereas extensive variables scale with the size of the system. So numbers of moles, obviously, if you double the size of the system, you will double the number of moles or molecules, same with the volume, same with the entropy. So there are these interrelations that we know from classical thermodynamics. I don't know, have you ever seen this diagram before? Some of you might have seen it. It's merely a memorandum to just remember these relations. Have you seen this before? Anyone? If you have, you can just give me a thumbs up. No, okay. Ah, one person has seen it. Yeah, tell you what has seen it. Okay, good. So for the others, this is a, as I said, a simple memorandum, right? It's not magic or anything. So you draw this this box with these arrows. We'll talk about what these represent in a moment. And there is this phrase that you can use to remember. So you start writing the variables and thermodynamic potentials from here. And the phrase, the memorable phrase is, good physicists have studied under very able teachers. Okay, so, right, so this way you can just create the little schematic here, and then here is how you can get these relations that interrelate all of these variables. So let's talk about energy. The variables that are close to the energy, right, next to the energy, so volume and entropy, are the natural variables of this thermodynamic potential, right, the internal energy. So in addition to these, of course, you always have the number of molecules or number of moles, which always appears in a term like this. So when I write these equations, the first thing I do is write the total differential of the potential I'm interested in, like du in this case, equals something times ds plus something else times dv, right? ds, dv, because these are the natural variables of energy. Now, the something that multiplies these ds and dvs, right? And of course, from mathematics, you remember that the total differential of a variable can be expressed with respect to partial derivatives, right? Times the differentials of the variables that are the natural variables of this function. So then let's talk about the derivatives. You see that for s, this arrow shows towards the temperature here. So this means that the following relation, so this kind of relation is encoded like this. So du ds, right? So the partial derivative of u with respect to s is equal to the temperature. And if the arrow points from the natural variable to the derivative, then this means that you have a positive sign. So I have du ds equals plus temperature. Whereas if you have the opposite, right? So in this case, the arrow points from the derivative to the natural variable, then this means that we will need a minus sign over here. So du dv equals p with a minus sign, right? So this, as I said, this is just a way to encode all these thermodynamic relations into this nice little schematic. So if you understand how this works, then we can find similar relations for other thermodynamic potentials. Let's talk about enthalpy. Where is enthalpy? Here. So what are the natural variables? Entropy and pressure. So I know that dH is going to be something times ds plus something else times dp. Right, so what are these somethings that I said? Let's go follow the arrow. So temperature times ds, and the arrow is pointing from the natural variable to the derivative, so it's a plus sign. And then v times dp, as I've shown here. And again, the direction of the arrow indicates a positive sign. Let's look at Gibbs free energy. Gibbs free energy is here, natural variables, temperature, pressure. So dg is equal to minus s times dt, right? Because of the arrow pointing from the derivative to the natural variable. plus V, right, times dP, plus this term which always arises. As I said, in all of the thermodynamic potentials, we have sum for 1 up to the number of species that we have in our system. And what are we summing? Mu I, the chemical potential of the species, times dNi, the change in the number of moles of that species. Yeah. So any questions so far? No, all good. So remember this, it's a very useful schematic. And remember the phrase, good physicists have studied under very able teachers. And then from these relations, you can come up with another memorandum type of schematic, which is shown here, and it relates the different variables and chemical potentials together. So this shows all the contributions, right? So I always remember that the Helmholtz free energy is the smallest one of all. And then I have the PV and the TS terms. So if I sum up the Helmholtz free energy plus these two terms, I get the enthalpy, which is the quote unquote largest of all of them. And then A plus TS gives me the internal energy, and then A plus PV gives me the Gibbs free energy. Yeah, so all of these relations can be easily derived. One more thing before we go and talk about StatMech, the Euler theorem, which is a theorem that tells us something about first order homogeneous functions. So what are these functions? A first order homogeneous function satisfies the following property. So first of all, this is going to be a multi-variable function. So it's a function of x1, x2, x3 up to xn. So if I multiply the value of x1 with a lambda, constant lambda, and the value of x2 with the same constant, and all of the values of the variables with this constant lambda. So I'm trying to find this, then the function satisfies that this expression is exactly equal to lambda times the function evaluated at x1, x2, x3 up to xn, right? Now, why is this useful? Remember what we were talking about a moment ago. I said, imagine, I was talking about this in the context of extensive variables. Imagine our box with the ice cube and the water and the vapor. I double the size of the system. So I double the volume and the entropy and all of the other extensive variables. And this way, I will also double the internal energy of the system. So the application to that, which we will discuss in a moment, will have to do with a thermodynamic potential that is also an extensive variable. So the internal energy is a function of extensive variables, and it is also an extensive variable itself. So this means that the internal energy satisfies this condition. And if this is true, Euler's theorem from mathematics tells us that the function can be expressed as the sum over all of these variables, right? All of these variables of these derivatives times the values of these variables, right? So this sum is df dx1 with everything else constant times x1 plus df dx2, everything else constant times x2 plus etc. Yeah. So let's try to apply it for the internal energy. So if we apply it, we get that U, the internal energy, because it's a first order homogeneous function of extensive variables, can be written as du dv with everything else constant times the volume plus du ds times the entropy plus the sum, right, du dni times ni, and we sum over all the species that we have in the system. But then from the equations that we discussed earlier, we know, for example, that du dv is equal to minus pressure, du ds equals plus temperature, and of course, this is chemical potential. So this way, we end up with this relation, which is a very special relation an application of the Euler's theorem for the internal energy. And we're going to use this later when we talk about properties of functions in statistical mechanics. Okay, any questions so far? All good, because now we're going to go back to the original problem I posed, namely, how do we relate the microscopic world with the macroscopic world? And as I mentioned a moment ago, we know the laws that these small particles obey, right? The atoms and the molecules. So in the quantum mechanical description of nature, we have the Schrödinger equation that, for instance, the electrons are obeying. Then if we go with the classical description of what the nuclei do, we can write a model based on Newton's laws of motion with, of course, known interparticle interactions. And then the question is, if we know these things, what are the observable properties of the system? And the system, of course, consists of a very large number of particles, atoms, molecules, electrons. So the problem is that, you know, if you have 1 mole of water, you have 10 to the 23 molecules of water in there, right? So you have a huge number of particles. Imagine how many atoms and electrons you have in that system. So we, you know, to solve the microscopic equations of motion, like Schrödinger equation or Newton's laws, it's impossible. Even with the strongest supercomputers nowadays, you cannot do simulations, molecular dynamic simulations with 10 to the 23 particles. But what we can do is invoke statistical arguments to go from the micro to the macroscopic world. And this is what we're going to talk about now. So we'll talk about the statistical mechanics framework, and we will introduce these concepts: microstates, Hamiltonians, and averaging approaches. So key to all of these statistical arguments is how frequently a microstate is visited. So we need to discuss a bit what is a microstate. Now, let's say we have a classical description of our ice cube. So for those of you who might be doing molecular dynamics, by the way, who do we have anybody who is going to be doing molecular dynamics? Or are you guys only
I'm going to use it.
Yeah, okay, great. So in the molecular dynamics description, you can have, so there are several flavors. Yeah, you can do ab initio molecular dynamics, but in my case, I'm going to assume that we already know the interparticle interactions. So the particles would be either the molecules, all of them, if we want a lumped kind of description, or the atoms, oxygen atoms and hydrogen atoms, if we want a more detailed description, higher fidelity. The point is that the microstate contains all the information about the system, and in this description, the information is summarized in the positions of the particles, each and every one of the atoms that we have in the system, right, for the fine-grained description, but also the momenta. So this R1 is a vector with 3 values, x, y, and z, which indicates the position in the x, y, and z coordinates, right, in our system. R2, the positions for the second atom, R3 for the third atom, etc. Then P1, P2, P3, etc. These are the momenta, right? Velocity times mass of the first particle, 3 components again, x, y, z, second particle, etc. Now, so this for the classical description. If we're looking into a quantum description, right, quantum mechanical description, a microstate would contain information about the quantum states of each particle. In this case, I'm showing an example. This is a bunch of particles that do not interact with each other, and they exist in a known potential. In this case, this is a harmonic potential. And if you remember from your quantum mechanics, the solution to this problem, right, quantum harmonic oscillator, gives us discrete energy levels, which are equispaced. So if you know the quantum number, then there is a very simple linear relation that gives you the energy of that state. Yeah. So the microstate would contain all information about the quantum state of each particle in our system, And of course, it suffices to know the quantum numbers of each one of these particles. So this is what I put in this vector here. Okay, so this what is the microstate, right? The microstate gives us or encodes all the information about every single particle in our system. Now, what about Hamiltonian? Well, the Hamiltonian is simply the energy of a microstate. Yeah. So when I say of a microstate, I want to stress this, right? Don't confuse Hamiltonians with thermodynamic potentials. The thermodynamic potentials are at the macrostate. The Hamiltonians are energies at the microstate. Yeah. So the classical Hamiltonian of the ice cube would contain this term here, which is basically the kinetic energy, well, the sum of kinetic energies for all the particles in the system, plus this term here, which is the potential energy, which is a function of the positions of these atoms in the system. Now, what if I was not looking at an ice cube? What if I was looking at an ideal gas? What do you think the Hamiltonian would look like?
It could lose the potential because in an ideal gas, the particles don't interact.
Exactly.
Yeah.
So in an ideal gas, we don't have this term here. We only have these terms, the kinetic energies. Yeah, exactly, because the particles do not interact. So this is a classical Hamiltonian, and then for the quantum Hamiltonian, for the particles that are non-interacting, we have something like this. Again, the kinetic energy term, and of course in quantum mechanics we have operators, right? So the kinetic energy is expressed as an operator that operates on the wave function. So this is the operator here. And of course, the known potential, again, we're going to have a bunch of interactions with the particles, right? The interaction is now between each particle and the potential. We said that we have non-interacting particles in this case. So this is one simple Hamiltonian for this system, a bunch of particles in a known potential, like a harmonic potential here. And of course, there are more complicated Hamiltonians, like you might have seen, we have seen the Hamiltonian that we put in the Schrödinger equation that we solve for the electrons going about their motion around nuclei and forming molecules, etc. Right? So this is a much simpler Hamiltonian here. Okay, now let's talk a bit about averaging, which these averaging operations are key in taking us from the microscopic world to the macroscopic world. So here's my ice cube again. I'm assuming that I am doing some molecular dynamics calculation, and this is how the state of the system changes as the simulation progresses. So this is really some sort of random walk in a very highly dimensional space. So you see, I have all the positions of all the atoms here, R1, 2, 3, and dot, dot, dot means up to Rn, and n is a very large number. And then here the momenta. So this is the phase space, as it's called, of the system, in which the microstate sort of lives, right, resides in this highly dimensional space. And as you saw, we have this kind of random walk, right? So this random walk is really the wandering about the phase space. Phase space has the positions and the momenta. The state space would have only the positions, right? So it depends. Yeah, it depends on the convention. Okay, so the point is that we want to do some averaging and find a macroscopic quantity as an average of instances, as an average of samples, right? So we are looking into this wandering. We're taking a sample at some time. We're taking a sample at some other time. This is one way to do it, right? Sampling over time. Another way to do it is create an ensemble such simulations. And then you can do the averaging over all the ensemble. The ensemble is basically a bunch of, it's a set of copies of the original system that may be initialized with different initial condition and go around the state space as well. The bottom line is that this averaging operation can be written like that. This G observable, right, the observable macroscopic quantity is equal to this, this sample average, 1 over number of samples, sum for alpha going from 1 up to the number of samples, G of alpha, right? These are the measurements that we take, irrespective of whether the measurements are over time or over an ensemble. So each one of these measurements yields a value for the observable, and then we average them out. Now, there are two fundamental postulates in statistical mechanics that we're going to also invoke later when we're discussing averaging operations. First of all, the principle of equal weights. This it's a simple principle, but with very important consequences. So what does the principle say? That it says that microstates that have equal energy are visited with the same frequency. Right. So if we have two states, here is our states or phase space again. If we have two spaces that have exactly the same energy, we expect that in this wandering, they're going to be visited with the same frequency, the same probability, effectively. Yeah. The second postulate is the ergodic hypothesis. So a moment ago, I was talking about these two different ways of doing sampling. One sampling over time, another one sampling over copies of the system, over ensembles. So the ergodic hypothesis says that averages over time are equal with ensemble averages. So these are the two principles that we're going to use, and we'll see what kind of implications they have in the equations that we derive. Any questions about this or anything we've discussed so far? No? All good? Okay, so let us now consider the time average of an observable. So here's we will assume that this is a time average, the way I've written it here. Here is our observable. We plot it over time. We see this kind of stochastic random walk, right? We have the fluctuations. Okay, so we're going to try to partition the sum as follows. So this is sum over samples, but right, so this so this sum over samples, but then we can partition it with respect to the states. So now I'm taking this sample and I'm this averaging operation, and I'm recasting the sum as a sum over states. So chi now is an index for the states that this system goes through. So this 1 over n goes in, and then I have here the number of times the state Sx is observed in the n samples. So I think you would agree with me that if I have, let's say, the one state 455, let's say I have a way to number them, has appeared maybe 10 times in this sum. Yeah. So then this, the contribution of this state 455 would be 10 times the observable, the value of the observable at that state, divided by n. This is exactly what this equation tells me. I count the number of times that state is visited, right, among the n samples that I have, divide by this n over here, times this observable evaluated at that state. But this thing here now, if you think about it, is really the probability, right? It's an estimate of the probability of visiting that state Sx. And this is what I have written here. So G observable now is a sum over all the states that are visited. When what are we summing? The probability times the observable evaluated at that state, right? It is the probability of visiting that state. And we're going to denote this right? To simplify our notation, we will denote it as a bracket average. And we will refer to it as an ensemble average. Okay, so any questions about this? Looks reasonable, I hope. Okay, so what is the ensemble again? Copies of a system, each one in a potentially different microstate. Right, and then we perform this averaging over the ensemble by summing over the states. Now, so this is the formal definition of the ensemble. As I said, collection or assembly of all possible microstates, which the system can visit given some macroscopic constraints. So macroscopic constraints would be, for instance, keeping the energy fixed and the number of particles fixed and the volume fixed, right? So this ensemble is called the microcanonical ensemble, and it contains all the states that have fixed number of molecules, fixed volume, and fixed energy. We can impose a different constraint, like we can have states with fixed number of molecules and volume, and states that have the same temperature. Now, you will realize that this, now I'm getting a bit into a gray area, because temperature is obviously a macroscopic quantity. But we will see that essentially the canonical ensemble is going to contain a lot of states that are possibly visited, but there is a probability over these states that ensures that the macroscopic temperature of the system, the macroscopic temperature that we would measure, is fixed at a certain value, right, T here. So, and this is an important observation I wanted to highlight, that an ensemble is a bit more than a collection assembly of states, right? It also comes with a probability measure over all these states. And this is what I have here. State 1 with probability P1, state 2 with probability P2, etc. So an ensemble is a collection of states. In addition, you have a probability measure over all these states that tells you how frequently these are visited. And of course, according to the first postulate of statistical mechanics, equal energies would mean equal probabilities for these states to be visited. So these are the two very widely used ensembles. There is a last one that we will talk about today, the grand canonical ensemble, which includes all states with fixed chemical potential, right? So we don't fix the number of molecules anymore, or number of particles. We fix the chemical potential, and we also fix the volume and the temperature. And this is called the grand canonical ensemble. So in the last part of this presentation, we will talk about these statistical mechanical ensembles one at a time to try to understand how we can perform averaging operations using these ensembles. And we will use, in the end, we're going to use the equations that we find to calculate properties of materials like monatomic ideal gas, diatomic ideal gas, etc. So we're going to start with the simplest one, the microcanonical ensemble, in which we fix the number of particles, the volume, and the energy. So since all of these microstates have the same energy, they're visited with equal probability. How many such microstates do we have? If we know that number, we know that the probability of visiting one of these states is 1 over the number of these states. So this number is called the degeneracy of the state, and this for discrete systems, of course. So we define the degeneracy as the number of microstates with n particles, v, volume, and energy, E. Right, and this, of course, this degeneracy is going to be a function of these three variables. So in order, of course, to keep the energy and the number of particles constant, this means that our system cannot exchange matter with its surroundings and cannot exchange any heat with its surroundings. Right, so it's an insulated or isolated system. So if we're looking into a system with continuous states, continuous state space, we can define something similar to the degeneracy. It's called the density of states, which is really the number of microstates with number of particles n, volume v, and energy between E and E plus dE. And this density of states, I put a little dash over there to indicate that this is a density. So it has units of 1 over energy. And yeah, so the density of states times this differential in the energy will give us the number of microstates with these characteristics. Okay, so these are the two kind of equivalent representations of the degeneracy for discrete systems and continuous systems in which we have the density of states. Now we're going to deal with the discrete systems, which are slightly easier. So we're going to deal with the degeneracy and the probability of each microstate, right? P chi is for that state, is equal to 1 over the degeneracy, very simple. And of course, we know that states that are that do not have this number of particles or this energy have probability of 0, right? Any state that is not in the ensemble has a probability of 0. And of course, we know that for continuous systems, this px would be a probability density, and this omega would be a density of states, but this is fine. We're going to keep the discussion simple, therefore we will deal with the discrete case, but similar equations hold for the continuous systems. So, okay, this is all very nice, but then you may ask me, okay, how is this useful? In the end of the day, we're going to have an astronomical or super astronomical number of states that exist in this ensemble. So how can we say anything about the let's say the enthalpy of the system or the entropy of the system, etc. So I just talked about entropy, and there is indeed a way to define the entropy in the microcanonical ensemble using a very famous formula. Right, this formula S equals KB times the logarithm of the degeneracy. What is KB? The Boltzmann constant, named after this guy here, Ludwig Edward Boltzmann, who developed this equation, which, as far as I remember, it has also been inscribed on his tomb. So so this is KB, Boltzmann constant, which has these values here in different units. And what is interesting to see is that this is a valid definition of entropy as an extensive variable. So let's say that we had two systems, right? One system A, one system B. We combine them together in such a way that they don't interact with each other. They're just independent. So then what would be the degeneracy of the composite system? Do you guys understand this formula here? So I say that the degeneracy is going to be the product of these two degeneracies. Why is that? So here is system A, here is system B, and I know the degeneracy of system A, namely the number of microstates with this number of particles, energy, and volume, and then same for system B. All right, and then I claim that the degeneracy of the composite system, which of course this degeneracy will have to be evaluated for the sum of number of particles, right? The sum of the volume, etc. This degeneracy is going to be equal to the product of these degeneracies. Why is that? It's basically because of combinatorics, if you think about it. So every one of these, so to create one state of the composite system, I can take one state of this system A, combine it with all the states of system B, then I can take the next state of system A, combine it with any of the states of system B. All right, so if I do that, if you think about it, in the end, you're going to have a possible number of microstates for the composite system, which is equal to the product of numbers of microstates for system A and system B. You guys agree, or is this counterintuitive?
It makes sense, but this is only valid if the systems are independent, right?
Yes, exactly. Yeah. And I say this explicitly here, two independent subsystems. Yeah. So if you have dependencies, so if you were to, let's say, put these systems next to each other and maybe like remove the partitioning, then it depends. So you might have, let's say, if you had solid state systems, then you might have some error because of the interaction at the interface, but this error could be presumed to be very, very small. So this equation would also hold in an approximate way. Yeah, but yes, it exactly holds for independent subsystems. So if this is fine, then, well, simply the logarithm of a product is the sum of the logarithms from mathematics. And therefore, the entropy of the composite system is simply KB times this thing, which breaks into log of omega A plus log of omega B, which is the entropy of A plus the entropy of B. Yeah. So this definition satisfies the extensive property of the entropy. Now, we can trivially see that the internal energy of the system is going to be equal to this energy. So sometimes I refer to this as internal energy, sometimes as thermal energy. For our discussions, it's the same thing. So U is equal to E, right? So this thermodynamic potential is equal to this energy that we fix the system in. And then if we want to find the temperature, we can use a thermodynamic relation, going back to our memorandum on classical thermodynamics. So temperature is equal to the partial derivative of U with respect to S for given volume, given number of particles. Okay, that's fine. Then we know that the entropy has already been expressed with respect to this K log omega relation. And if we do the differentiation, then we're going to find that this beta parameter, which is called inverse temperature and is equal to 1 over kBT, is equal to the derivative of the logarithm of the degeneracy with respect to the energy, keeping V and M constant. So this is, right, so essentially this is a way to calculate the temperature because KB is of course a constant. Now for macroscopic systems encountered in nature for which a classical description is good enough, beta is greater than 0, right? So as we increase the energy, we are able to access more and more states. This is what this means. So the temperature is positive as we expect. There is a bit of a pathological situation for some quantum systems in which what I just said is not true. So as you try to increase the energy of the system, you may decrease the number of possible states. One example is if you have a bunch of spins, the Ising model, for instance, right? So the Ising model is a prototype for magnets. You have a lattice model, and for each one of the positions of the lattice, you have a spin variable, so spin up or spin down. So if you increase the temperature, the system becomes more and more disordered. And let's say that you had a magnetic field which would tend to align all the spins in a certain direction. So the point is that if you increase the temperature, the spins are fluctuating, so they try to kind of counteract this magnetic field, and you get more entropy in the system. So for higher energies, you would get more entropy. But then if you increase the energy even more, right? So in the more disordered state, you have half spins up, half spins down. in order to increase the entropy even more, this means that you have to have more spins opposite from the magnetic field that you put in, which means that at some point you're going to start having or in the worst case scenario, you're going to have the predominant population of spins being opposite to the magnetic field that you want. But then this means that your entropy there is going to be decreasing because there are fewer ways to arrange these spins. If you have like 90% spins up, 10% spins down, you have fewer ways to arrange these in distinct combinations. So as the energy increases, the entropy decreases in the system. So this is, in this case, you're going to have a negative temperature. And this is fine. I mean, it is known that in physics, in quantum systems like the one I described, with two states, spin up, spin down, for each one of the particles in your system, you can have negative temperatures. So this phenomenon is called population inversion, and it also has applications in laser physics. But there is a bit of a catch here that you cannot get to these negative temperatures with any thermal equilibration of the system. You're getting into situations like this when you're looking into systems that are driven far from equilibrium. So if you're interested in that more, you can Google this phenomenon, population inversion and negative temperatures, and you can learn more about it. Okay, now as a final thing in the microcanonical ensemble, we're going to talk about the pressure. We already know that we said before that the internal energy is equal to the energy of that ensemble. The pressure from classical thermodynamics is equal to minus the partial derivative of energy with respect to volume, keeping entropy and number of particles the same. So the point here is that this energy, for instance, in the quantum particle in a box, would be affected by the volume. So the energy levels are essentially affected by the volume, and this is what would create pressure. To give you an example, here is a quantum particle in a box. This is a small box, right? Going from minus whatever I have, like minus 8 angstroms up to 8 angstroms here. And here are the energy levels for the set of values that I used for the mass of particle and this length. So if I now change the volume of the system, in this one-dimensional system, I'm going to change the length of the box. You will see that I have a different spectrum of energy levels here. Do you guys remember the particle in a box from your quantum mechanics? Yeah? Okay, so this is the relation between energy, quantum number, and, well, Planck constant, mass of the particle, and the length. So the bottom line here is that when you change the volume, you change the energy levels, and this is what creates some, it leads to this pressure, right? A non-zero value for the pressure. So since we now have the entropy, KB times log omega, the pressure from this relation, U, trivially equal to the energy, and the temperature that we discussed a moment ago in the context of this beta, the inverse temperature. Since we have these, we can calculate any other thermodynamic quantity, right? So if you go back to the schematic that we showed and the relations between the thermodynamic potentials, if you have these, anything else can be calculated. So by starting from this equation, the fundamental equation here by Boltzmann, we were able to essentially derive equations for any thermodynamic observable in our system, may it be entropy, pressure, enthalpy, Gibbs free energy, etc. Okay, so this is the power of statistical mechanics. Using some fundamental equations, you can get expressions for all these thermodynamic potentials and the variables. Okay, we're 5 minutes before 2 p.m. Would you like to take a small break and we can resume with the canonical ensemble?
Yeah.
Yeah?
Good.
Okay. And think about any questions you might want to ask. So we can resume at 2 p.m. Yeah. So I'm going to, I think we're going to still continue recording. I cannot pause the recording, but that's fine. Actually, maybe I can. All right, so let's resume. Okay, so we talked about the microcanonical ensemble. Now let's move on to the canonical ensemble. There is quite a bit of math and a bit of a, let's say, thought process to prove the final relation that gives us probability with respect to the energy here. I'm going to highlight the main parts, right, of this thought process. But if you want me to go into the details, by all means, please let me know. So the canonical ensemble is an ensemble. Okay, oh yeah, so now it's moving. So it's an ensemble in which we have microstates with fixed volume, number of molecules, and we also have these. So we have our system being in thermal equilibrium with a heat bath, which means that the temperature of the small system here is almost equal to a constant, namely the constant, the temperature of the heat bath. So why does this happen? Well, as I said, there is the heat bath and the small system is in thermodynamic equilibrium with that. And of course, there is the energy can fluctuate. So you can have energy going from the heat bath into the system or the opposite. So the in these energy fluctuations, we're going to basically get some fluctuations of the temperature around a fixed temperature, since we assume that the heat bath is much, much larger than the small system here, right? So this is a key assumption. We have much more energy inside the heat bath than in the small system. This means that if the heat bath is losing a little bit of thermal energy, its temperature remains almost the same. And this is how we keep everything at an almost, right? This is how we keep the small system as well at an almost constant temperature, because it's in thermodynamic equilibrium with the heat bath that is at a constant temperature to an excellent approximation. Right, so this is a key assumption here. The heat bath is much, much larger than the system. Now we're interested in the probability that each microstate of the small system is visited in this ensemble. So the first thing to do is to consider this large system as an isolated system, right, insulated. So this means that this large system, which involves the heat bath and the small system, is or can be treated in terms of the canonical ensemble. What is the total energy of the large system? Well, clearly, it's the energy of the bath, right? This energy of the bath here, plus the energy of the small system. And this is equal to the total energy of the large system, which is assumed to be constant, right, by applying this insulation here. Okay, so then we can talk about the energy states, right? So the energy of the large system, that includes all of them, is constant. These are the states of the large system. How do I create these states? I put together the state of the small system and the state of the bath. So the state of the small system may be S1, the state of the bath, S1 bath or S2 bath, etc. So I have combinations of states for the small system and the bath, and all of them have the same combined energy. Okay, so now the combinations of these microstates, in which, of course, the energies of these two sums up to energy, right? E, are indeed valid, accessible states of the large system in the microcanonical ensemble. Okay, now the first important component or element in this thought process is that we take the bath and the small system as insulated, right? One composite system, which is insulated, that can be treated in the microcanonical ensemble. This way, we can use the formulas we derived for the microcanonical ensemble to try to find what is going on at the small system. So we're considering a slightly different partitioning of the states, as I say here. So I'm plotting now energy of the small system. When I say our system, it means this small system here. So this can be in energy E1, energy E2, E3, etc. And these are some combinations of the energies of the small system and the bath that give us a total energy equal to E, right? We want the sum to be always constant. So I can do this partitioning, and then we're going to look into what is happening if we fix the system, the small system, in a state X or chi, yeah. So here's our small system. We fix it in state chi. And then if we do this, the accessible states of the entire system, the composite system, are basically only the states of the bath. Agreed? So if we do that, then we have that the degeneracy for the bath, right? So the degeneracy of the whole system, which is a function of the energy of the bath, is going to be equal to this omega of energy total minus the energy of the small system, because these sum up to this energy. And then we're going to try to apply the principle of equal weights and derive the probability of this state chi of the system. So this is the result here. So as we said earlier when we were talking about the microcanonical ensemble, the probability is proportional to the degeneracy. So the probability of having this system, the small system, in fixed state chi is proportional to essentially the probability, the degeneracy of the energy states of the bath, right? These energy states that have energy E bath. And trivially, this energy of the bath is energy minus energy of the small system. So now, right, so this is the next important part in our thought process. We apply the principle of equal weights to the degeneracy of the energy states of the bath, right? So if we do that, then the probability of state S chi for the small system in the canonical ensemble is proportional to this degeneracy. Now, the problem is that this degeneracy for the bath energy level is kind of a weird function. It's very rapidly increasing. We would like to have something a bit more well-behaved. So, okay, so this just summarizes what I was saying, right? This is the energy of the degeneracy of the bath energy level, the energy of the large system, the composite system. This little thing is the energy of the small system. And this is a badly behaved function, so we're going to do a little trick to make it a bit more well-behaved. So the first thing I do here is a trivial mathematical operation, e to the log of this thing. Clearly, this is equal to omega of A minus E chi. Yeah, this is just trivial. But now I want to focus my attention on this logarithm of this omega, which is a more well-behaved function. So I'm going to introduce a Taylor expansion. Why can I do this? Because E is a large number compared to E chi. So E chi is something small, and I can introduce a Taylor expansion for this logarithm of omega around E with E chi as a small perturbation. Yeah. So the Taylor expansion tells me that this logarithm of this thing is equal to logarithm of omega evaluated at E, right? In the zeroth order approximation, E chi is equal to 0, minus E chi times the derivative of this thing, right? The derivative of this log, this function that I want to approximate over the energy, plus higher order terms. Now, if you think about it, what we care about is the E chi, right? So we want to, in the end, find an expression that tells us probability of visiting that state is equal to some function of E chi. So this thing is effectively a constant. And this thing here, we already know from the equations that we discussed in the microcanonical ensemble. This is clearly equal to the inverse temperature. So then we end up with an equation that looks like this. Okay, let me go back here. Right, so this logarithm, we said that this term is going to be a constant, and then we have E chi times beta. So effectively, the probability of visiting the state is proportional to E to the minus beta times E chi. So the probability of the small system, this thing here, visiting state chi is proportional to E to the minus inverse temperature times the energy of that state. And this thing is minus energy divided by kBT, essentially. So this equation was also named after Boltzmann, and it's called the canonical or Boltzmann distribution law. So you might have seen this before, but maybe without this kind of proof or this thought process. So hopefully this clarifies the way we reached this conclusion. Any questions before we move on? Yeah, looks clear. Okay, so I said here this is proportional, but what is the proportionality constant? Well, we know that the probability is a normalized quantity. So if we sum over all the states, what are we summing? The probabilities. This sum is equal to 1. So effectively, sum of E to the minus beta times E chi for all states chi is equal to 1. And this sum, right, I just showed, I'm showing it here. This sum, Q, is called the partition function for the canonical ensemble. So then the probability is simply 1 over the partition function times E to the minus beta times E chi. So Q is the canonical partition function. It is a function of number of particles, volume, and temperature, because these are the variables that we keep that are known in the canonical ensemble. We keep them fixed. And equivalently, we can have, instead of T, we can have beta, inverse temperature, right? And of course, if the partition function of a system is known, we can derive any other thermodynamic quantity. This is true for any ensemble. If you know the partition function, you know pretty much everything. So you can, in principle, at least, because the mathematics could be complicated. But in principle, you can derive any thermodynamic quantity if you know the partition function. Okay, so let's look at an example. We would like to derive the internal or thermal energy of a system that exists in the canonical ensemble. So a system which has a fixed number of particles, fixed volume, and temperature known. Okay, so how do we do this? Via averaging. U is going to be equal to the average energy, and this is equal to sum over all the states of what is the energy at that state times the probability that we will visit that state. Right, simple. So this is just an averaging operation. But then here is the kind of the magic that happens, right? This average, if you think about it, is this expression here. The magic will happen in a moment, but let's look at this, this expression closely. So this energy is the quantity being averaged, and everything else, this thing here, is the probability of the microstate chi. Agreed. This is, remember we said that the probability is proportional to this term, and what is the proportionality constant? It's the partition function. This is the partition function here. So 1 over partition function times E to the minus beta E chi. This is exactly the probability that we saw in the previous slide a moment ago, this thing here. All right, so now I think you will agree with me that this thing and this thing, right, this E and this exponential here are, you know, like brothers. So how can I get this energy from this exponential? Do you agree that if I differentiate this exponential with respect to minus beta, this derivative is going to give me an energy over there? It's obvious. So by this, and after substituting this expression with the canonical partition function, I arrive at this equation here. Energy is equal to 1 over Q, partition function, canonical partition function, times sum of these things here. But then I think you would also agree with me that we can interchange the sum with the derivative. These are linear operators, and provided that we don't have anything pathological happening, like these terms are well behaved, then I can interchange the differentiation, partial differentiation, with the summation, and I can get this thing here. I also put this minus sign outside here. And what is this? Do you recognize this term here?
The partition function?
Exactly. It's actually the log of the part.
Oh yeah.
Well, no, sorry. It is the partition function, but then I combine it with 1 over Q, and I get the log.
Okay.
Right.
Okay.
Remember the logarithmic derivative, d log Q would be 1 over Q times the derivative of Q, whatever we had into the argument of the logarithm. So, so you can use equivalently this expression, or minus 1 over Q, dq d beta, same thing. Of course, keeping number of molecules and volume the same. So this goes back to the discussion we had a moment ago, and I was claiming that if you know the partition function, you know everything. So we already saw that we can calculate the internal or thermal energy. Now let's look at how we calculate entropy. For the entropy, we use another equation here, which was it is a general equation for entropy, valid for any ensemble, and it was derived by Josiah Willard Gibbs. There is quite a lot of like deep mathematical, let's say, underpinnings behind this, having to do with information theory and things like that. But we're not going to go into the details. We're going to take this for granted, and I think you would agree with me that since we know the if we know the partition function, we know the probability as well, and we can apply this formula here and get the entropy. Now, I would like you to do as homework this proof here, so that in the microcanonical ensemble, this equation simplifies to the Boltzmann formula. I don't know if anybody did this, because presumably you had watched at least some of the lectures and you might have tried it. Did you try to do this? No? That's fine. It's very easy to prove. So do it as homework just to convince yourself that the Boltzmann formula and this are the same for the microcanonical ensemble. Now, in the canonical ensemble, the probability is equal to this. So if I do the substitution for the probability, I get this expression here. Right, so P 1 over Q times this thing, and then the log of the probability will give me two terms. Remember the properties of your logarithms. Log of the product is sum of logarithms, and then log of 1 over something is, you get a minus sign here, right? Minus log of that something. So this gives me essentially this expression over there. So then I can do a little bit of math. And as I said, I'm going to skip the detailed mathematical derivations unless you really want me to show everything. You can follow the derivations at home. I'm also discussing this in the video lectures. So in the end, what you're going to get is entropy equals U over temperature, right? Internal energy over temperature, plus KB log Q. Now, this is interesting because this, I mean, okay, so I'm just doing a trivial reformulation here. So I multiply by temperature, so I get T times S equals U plus KT log Q. And this is interesting. Why? Because we know this from thermodynamics. We know a relation between the Helmholtz free energy and the internal energy, the temperature, and the entropy. Right? You see the memorandum from the classical thermodynamics that we did earlier. So let's look at the terms. U, right? We have U here. The TS can go to the right-hand side and it's going to appear with a minus sign. And then this KT is going to go to the left-hand side. And that basically will be the Helmholtz free energy. So what we have shown is that in the canonical ensemble, there is a simple relation between the Helmholtz free energy and the partition function, right? The canonical partition function. And this very simple relation. So now we can easily calculate the pressure because we know, again, from our thermodynamics classical thermal memorandum, we know that the partial derivative of the Helmholtz free energy with respect to volume, keeping number of molecules and temperature constant, is equal to minus pressure. So we can do the math. We said that A is equal to minus KT log Q. Right, so the pressure is equal to this derivative, and I just wanted to point out that the volume does not appear explicitly in Q, right? We said Q is a function of N. In this case, sorry, actually, yeah, this is NVT, right? So the point is that if I was to write the arguments here, it would appear. But the point I wanted to make is that it affects the energy levels. And this is similar to what we were discussing before, right? Remember this quantum particle in the box. So this, indeed, this derivative is going to give us a non-zero value because this is indeed the function of volume. Okay, so what we have so far is temperature, which we know because it's one of the variables that we fix in the canonical ensemble. We know the Helmholtz free energy, we know the pressure, and we know the entropy as well. So since we know all of these quantities, right, the entropy was derived here. Since we know all of these quantities, then we know pretty much everything, every other thermodynamic potential that we may be interested in. Any questions before we go into the grand canonical ensemble?
Hello, I'm a little bit confused with this exact physical meaning of the partition function. And it looks like degeneracy, but they are certainly different, I think.
So the partition function, yeah, I mean, the definition was here, right? Here, it is.
Yes,
okay.
yes.
So you want to know the physical meaning of the partition function.
Yes.
So yeah, that's I would say that the partition function does not relate to any directly measurable physical quantity. But what we could say is that, and that's why it's called the partition function, it gives you the partitioning on frequencies of visiting the state space, right? So if you look at these terms that we're summing, these are terms that are proportional to the probability.
Yes.
Right. So, and of course, the partition function is, as we said, the normalization condition. So if you have these terms which are proportional to the probability, then the partition function is summing all of these terms. So if you're looking into regions of your state space, so let's say that we don't know anything about probability yet. We have a very highly dimensional space with the states, all the possible states of the system. And then let's say I'm creating a small partition function, right? I'm summing over these states here in my state space. And this, I define it as Q1, partition, a fraction of the partition function that relates only to this area of the space. Then I'm doing the same thing with another area of the space, maybe here. So I have, again, a bunch of states, these states enclosed in this hyper box in the multi dimensions. And I summing these terms, e to the minus beta times energy, for these states here. And this I define it to be Q2. So if Q2 is larger than Q1, then this means that these states here have a higher probability of being visited, right?
Yes.
So that's why it's called it's called the partition function, even though we sum over everything. But the point is that it's this thing, if you divide the partition function into smaller sums, these smaller sums, right, are proportional to how frequently you're going to visit the states in which these sums relate, or which these sums pertain to. So
Okay.
it's like, yeah.
Yeah, I see. Thank you.
You see, so it's like you're breaking all the sort of the frequencies of visiting any state, you're breaking into small boxes, and if you sum everything together, you have this Q, which is useful because of all of these properties.
Okay.
But you're right, it's not directly relatable to anything else. You need to get all these fancy derivatives and other expressions to relate it to measurable quantities. Okay, any other questions? Okay, we'll talk about this. So the final ensemble we're going to talk about is the grand canonical ensemble, which is kind of similar to the canonical, but in this case, we also allow for matter exchange. Remember, in the canonical ensemble, we had an isolated big system that consisted of a heat bath and a smaller system which could exchange energy, thermal energy, with the heat bath. In this case, we have a heat bath, but also matter reservoir. So it's not only that we exchange heat, but we also exchange matter between these two systems, the bath and matter reservoir and the small system. So similar, okay, so the ensemble would comprise microstate, right? The ensemble consists of microstates with fixed volume, and energy and number of molecules can fluctuate as the system is in thermodynamic equilibrium with this heat bath and matter reservoir, right? Heat bath at temperature T, matter reservoir that is kept at the chemical potential nu. And we, as previously, we assume that the heat bath and the matter reservoir are much, much larger than our system, and the system can be treated as an isolated system, and then we can apply a very similar thought process as we did for the canonical ensemble. And if we do that, we're going to show that the probability of visiting a state in the grand canonical ensemble is equal to 1 over xi. This is this Greek letter xi, or xi in English, which is the grand canonical partition function, times e to the minus beta times e chi. This term we already saw previously in the canonical ensemble, but now there is another term, plus beta times nu, the chemical potential that we know, right? The chemical potential of the matter reservoir, times n chi, the number of particles in state chi. Yeah. And of course, this partition function is the sum of these terms here. And it's, again, the normalization constant for the probability. Okay, so this is the grand canonical partition function. It's a function of chemical potential, volume, and temperature, or equivalent chemical potential, volume, and inverse temperature, beta. And the in the microcanonical and canonical ensembles, the number of particles were fixed, whereas in the canonical ensemble, the grand canonical ensemble, the number of particles fluctuates, the chemical potential is fixed, and we can try to find the average number of particles in the grand canonical ensemble by doing, again, some averaging operation. What's the averaging operation? Well, here is this average of number of particles. Remember, brackets means I'm averaging over an ensemble. This is equal to 1 over Xi times this thing here. So remember this. So this e to the minus blah blah divided by Xi is the probability that we will visit state chi in the grand canonical ensemble times this quantity that we're averaging, number of particles in state chi. This is the average number of particles. But now again, the magic happens, right? See, n chi here, n chi over there. So this thing can be expressed as a derivative. What derivative? The derivative of this exponential term with respect to whatever is multiplying this n chi, namely this thing here. So this is our derivative. And again, this term is, so we can interchange again the differentiation with the summation. So we're going to get this, and now we have our partition function appearing again. And with this 1 over xi, we make it into this expression here. So this is the logarithmic derivative. So the average number of particles is equal to d log xi, the grand canonical partition function, d beta nu. Yeah. So similar things can be applied. Or similar like mathematics, we can apply to calculate other thermodynamic quantities. For example, the entropy. We use the Gibbs formula in this case. So we know the probabilities, and then after a bit of math, which is not too difficult, we end up with this expression here. Right, always remember beta is the inverse temperature 1 over kT. So this equation here is relating temperature, entropy, the partition function with the internal energy and chemical potential and number of particles. This number of particles is the average number of particles, right? I just dropped the brackets just for simplicity. So it's the macroscopic number of molecules. Now, here we can recall Euler's theorem, right? So let's try to see it again. I should have copied it probably, which was on slide 7. Right, so this was here. This is Euler's theorem. And if we have only one type of particles, this will be U equals minus PV plus TS plus nu times N. So if we go back to the slide that was previously, so just remember this thing here. Right, so if we apply the Euler theorem over there, we can substitute these terms here. So Ts, U, and nu times N. These things are going to give us P times V on the left-hand side of the equation using the Euler theorem. So then we end up with a nice expression that shows that the grand canonical partition function is related to pressure, volume, and temperature in a nice and simple way. Right, that looks like this. So you might have noticed that in all of the ensembles, in each one of the ensembles, there is some kind of almost natural function, right? So for the microcanonical ensemble, it's the entropy related to the degeneracy, which is the very simple relation in that case. Then for the canonical ensemble, we have the Helmholtz free energy related in a simple way with the partition function. And in this case, we have PV over temperature related in a simple way with the grand canonical partition function. And yeah, this applies also to other ensembles. So more complicated ensembles, again, have a simple relation with other thermodynamic potentials. This way you can use any ensemble that is convenient for your calculations in order to derive the equations of thermodynamics that you're interested in. There is a theorem that basically tells you that when you go towards very large systems, all of the ensembles are going to give you the same answer. right? So we're not going to go through the details of this. We're just going to accept it as a fact that for macroscopic systems, all of the ensembles give you the same answer for all the thermodynamic potentials and the thermodynamic variables, right? Like these, etc. Which is nice, of course, because this provides a solid foundation for statistical mechanics, right? Obviously, all of these ideas would be useless if you got different thermodynamic equations from one ensemble versus another ensemble, but this is not the case. So this is what I point out here in the take-home messages. Macroscopically, all ensembles give the same answers. As I said, we're not going to discuss this in more detail. We're just going to take it for a fact. But yeah, just to summarize this lecture, statistical mechanics is all about deriving expressions for macroscopic thermodynamic variables from microscopic laws, like the Schrödinger equation that will give us the energy levels, right? Or Newton's laws of motion, and then the Hamiltonians for these systems. There are two fundamental postulates, the principle of equal weights. So states with equal energies are visited equally frequently. And then there is the ergodic hypothesis that allows us to replace averages over time with averages over ensembles. So what are these ensembles? Collections of states that may be subject to certain macroscopic constraints. And on top of that, we also have probability measures in these ensembles. So commonly used ensembles are the microcanonical, in which we have a fixed number of particles, volume, and energy. Canonical ensemble, because we have in which we have a fixed number of particles, volume, and temperature, and then the grand canonical ensemble, in which we have known chemical potential and temperature, and also the volume of the system. Any questions about these things?
I have a question related to the last thing that you said about for a macroscopical system. Supposedly, all the ensembles will give you the same answer, but in the context of a simulation, how big has to be a simulation in order for all the ensembles to give you the same variable?
That's a good question, but I'm not sure I have an answer to that. But
it will vary for system to system.
It probably depends on the system, because if you think about it, yeah, I'm thinking out loud now, because I'm not sure if I have a definite answer to that. But for difficult systems in which you may have very long range order, you have spatial correlations, you may need to have extremely large systems to be able to get the right answer close to critical points. One example would be if you have a lattice system. It's called the lattice gas model. It's a very simple model. You have a lattice, like imagine a chessboard, and you have particles on these lattice sites. And if there are some, let's say, repulsive interactions, you may get a nice arrangement in which you place an adsorbate on a lattice site, the neighboring lattice sites are empty, and then the next adsorbate has to be placed on the second nearest neighbor site, if you had like only first nearest neighbor repulsive interaction. So if you simulate this system, you're going to end up with ordered phases that look like a nice kind of chessboard pattern, close to certain chemical potentials of the system that would give you the critical coverages. So if that is the case, if you're approaching some critical points in which you have like very long range order, then yeah, you might need to have much larger systems than in other systems that are mostly disordered in order to get the right answer. So I would say it probably depends quite a lot on the nature of the system you're simulating.
Okay. Yeah, thank you.
Yeah, I know that's not really an answer, but
no, but you have to figure it out for what you're going to do.
Exactly. Yeah. So there's no simple answer. Anything else? Any other questions? If not, we can move on to the next part, in which we're going to talk about specific systems, right? So can you guys see this? Am I still sharing my entire screen?
Yeah, I am seeing your
So,
PowerPoint.
yeah, okay, so F5, yes. All right. So you should be seeing a slide that says from partition functions to thermodynamic observables. And now I'm skipping to the first slide, yeah. So
I'm still
huh?
seeing your take-home messages from the
Okay.
last slide.
Okay, maybe I was not sharing the correct window there. How about now?
Yeah, now I see the first slide of a new PowerPoint.
Cool. Yeah. From partition functions to thermodynamic observables. Yeah. So all of this framework that we discussed can be used to find thermodynamic expressions for systems like the monatomic ideal gas, the diatomic ideal gas, adsorbates on the edge of a catalytic nanoparticle in the absence or in the presence of lateral interactions, etc., and more complicated systems. So these are some simple systems that I have chosen to discuss. And we're going to employ the common methodology that is outlined here. We will start from a Hamiltonian, which gives us, remember, the energies of microstates. We will choose an ensemble, and then we're going to perform the appropriate averaging operations, and we'll see some interesting things. Some of the relations we will derive you have already known for several years, and it's good to see that the framework of statistical mechanics can give us these relations. For instance, the ideal gas law. Okay, so we're going to start with the monatomic ideal gas. For instance, helium is an example of a very simple monatomic ideal gas. And then after that, we're going to discuss the diatomic gas case. A nice example would be bromine here. Okay, so what we're interested in is, first of all, deriving the ideal gas law from statistical mechanics principles, and then derive equations for the heat capacities of these gases, monatomic and diatomic. So the Hamiltonian for a classical gas with n molecules is like this, right? We talked about this in the first hour. And we also said that for an ideal, well, we also said that this is the kinetic energy and this is the potential energy. And we also said that for an ideal gas, we don't have any intermolecular interaction, so this term goes away. So we're going to use this in a moment. Now, we're going to choose to work in the canonical ensemble, in which we know the number of particles, the volume, and the temperature, and the classical partition function for this system will be like this. Notice that we have integrals here because the positions and the momenta, Can you see my pointer, by the way? Sorry, maybe you should just use this laser pointer. Okay. So both the positions and the momenta are continuous variables. So we're using this expression for the partition function. We integrate over all the possible positions and momenta. What are we integrating? E to the minus Hamiltonian, right? This is the energy of the microstate divided by KT. And then there is a bit of an additional term here. So 1 over n factorial is a term that corrects for the overcounting of the of this integral, because the molecules that we have in the system are indistinguishable, right? So since we have labeled these molecules with, you know, the labels molecule 1, molecule 2, or well, atom 1, atom 2, atom 3, etc. Since these molecules or atoms, monatomic ideal gas molecules, since these are indistinguishable, there are n factorial permutations for the labeling of the atoms that I have in the system, and that's why we have this overcounting when we write this integral. So 1 over n factorial corrects for this overcounting and gives us the classical partition function. The second thing that you see here, this h, right? So we talked about n factorial. The h gives an approximate count of quantum states and also makes the integral dimensionless, right? So this arises because of the fact that in reality, if you're looking into, remember the particle in a box, you have a discrete set of energy levels effectively. So this is what this thing takes into account. So it's an approximate correction for the number of quantum states that we have in a continuum part of the classical phase space. Okay, so this is the classical partition function then, and we know that we can evaluate this integral by breaking it into 2 terms. How do I do this? I'm just substituting this Hamiltonian here, right? So I will have e to the sum of something, which gives me a product. So this is the first part of the product, this thing here, and I integrate over the momenta, and this is the kinetic energy part. And then the second part is the potential energy, and I'm integrating over the positions. Right, so this arises from the kinetic energy term, and this sometimes is referred to as the configuration integral or configurational integral for the classical partition function. Now, for ideal gases, we said that this term is equal to 0. So this configurational integral is proportional to volume to the nth power. Why? Because e to the 0 is 1, and then I'm just integrating this bunch of position vectors, which effectively are going to give me, right, for each one of them, I'm going to have a volume term appearing. The integration, well, I write this as an indefinite integral, but you have to think of this as integration over all the possible states, right? So these are definite integrals. So in a box, this might go from 0 up to L for each one of the dimensions in the system, in the coordinates. So effectively, in the end, I'm going to get a term from here, which is equal to volume to the nth power. So this simplifies things for ideal gases because this term is trivial. Of course, for non-ideal gases or liquid states, liquid phases, or solids even, evaluating the configurational integral requires simulation, like the molecular dynamics simulation that we have been discussing a bit. And in our case, we're going to deal with ideal gases, which are simple. So here is the v to the nth power, right, from here. The terms that I carried over from the definition of the classical partition function, and then this thing here. Now, I note that we have a sum over there. So e to the sum of something becomes a product of terms, and here is what I'm doing right here. Product for I equals 1 to n, right, n particles in the system, of e to the minus this thing, right, which was the kinetic energy term over kT. So now, by noting that all particles are the same, all the masses are the same, right? So I have a monoatomic ideal gas like helium. So all masses are the same. I'm replacing this here, and then this, right? So these masses are the same. So all of these things, right? All of these integrals that I will have here are pretty much the same. They're basically this integral raised to the nth power, right, from the product here. So the product becomes a power because all of the terms are the same. Now, how are we going to calculate this integral? This is a Gaussian integral. So first of all, let's break this into the 3 dimensions. You see this D3P1 means P1X, P1Y, P1Z. This is what I'm doing here. And again, because of the fact that the space is isotropic, these integrals in the X, Y, Z directions are all the same. So I'm going to have the same integral raised to the 3rd power times this n over there. I have effectively this integral raised to the 3n power. Yeah, And this thing can be evaluated relatively easily from mathematics. Again, I'm going to skip the details, and I'm going to give you the final result. I mean, the details are quite easy to figure out. And the point is that this thing here is equal to 2 pi m k b t square root. So raised to the 3n power, I get all of this thing to the power 3n over 2, plus all the stuff I had carried over from the previous equations. So this is the ideal gas partition function. And again, this is an ideal gas, right? So n particles, n atoms of helium in a box of volume V, kept at temperature T, and the helium masses are these m here. Okay, so this is a kind of complicated equation. Why is this useful? I'm just simplifying it a bit here to introduce beta, which is the inverse temperature. Okay, so what can we do with this? Well, we can try to first of all calculate the thermal energy from the canonical ensemble formula, which was this thing here. So again, a bit of math. And in the end, I'm going to get this equation here, right? So the thermal energy is equal to minus the derivative over inverse temperature of log of a constant times beta to the minus 3n over 2 power. So now if you do this differentiation, you're going to end up with this expression here. Why is this? And of course, if we go substitute beta for inverse temperature, we get this. Why is this interesting? Because this gives us the heat capacity of the ideal gas. And you might have seen this equation before, right? So the heat capacity of the ideal monatomic gas is in textbooks. If you go and see any textbook, you're going to find this equation. CV is equal to 3 over 2 times R. So there is a relation between R and N Avogadro and KT. So R is equal to KB times N Avogadro. So the heat capacity is 3 over 2 times KB times N Avogadro, or equivalently, if you change the units, basically you get 3 over 2 times KB. So by using the statistical mechanics framework, we were just able to prove this equation that you have seen even probably in high school, if you did a little bit of statistical mechanics or physical chemistry. So we were able to prove this by using the Hamiltonian for the ideal gas and some averaging operations that we just learned how to perform. Now we can calculate the pressure from the canonical ensemble formula. Remember, the pressure is related to a partial derivative of Helmholtz free energy with respect to volume. So this is the equation. I'm showing it again. And if we do this differentiation, we find out that we found a very simple equation, which is shown here, right? The d log Q over V. This is the volume dependence of the partition function, right? And since you have log, right, log Q, you're going to get a bunch of terms that don't matter because they're constants and they die out when you differentiate. They get eliminated. And then you get n times log V. So that's how you get n in the numerator and then V in the denominator. Does this equation look familiar? It's the ideal gas law. All right, so P times V equals N over N Avogadro times RT. Yeah, or equivalently, PV equals KB times number of particles times T. So we recovered the ideal gas law, again, from very simple arguments. Essentially, the main argument here is that our ideal gas has only kinetic energy contributions to its Hamiltonian, and then the rest was just the recipe from the statistical mechanics framework. So we found the heat capacity of the ideal monatomic gas, and we recovered the ideal gas law by using these simple but powerful arguments and frameworks. Okay, so let's look at the entropy now. The entropy from thermodynamics can be calculated as the partial derivative of Helmholtz free energy with respect to temperature. We have a minus sign here, and you keep these things constant. So again, going back to the equation that relates the Helmholtz free energy with the partition function, remember this was minus kBT times log Q. So the minus has been eliminated here. So I have kBT log of the partition function of the ideal monatomic gas, all of this thing. Then the rest is math. Just remember, right? You can break the differentiation into a term that appears from here. This is a product of terms, and another term that appears from here. So I'm just doing the math for you. And in the end, you're going to end up with this. Let's pause for a moment here. So yeah, so here is an intermediate formula for the entropy, which is actually exact. Yeah. Now, in statistical mechanics, we're often going to use the so-called Stirling approximation for the logarithm of a factorial. So the approximation by Stirling tells us that the log of n factorial is approximately equal to n log n minus n. And of course, I said approximately equal to. There are some higher order terms that I have neglected here. So going back to this, if you apply the Stirling approximation and you do a little bit of math, you're going to end up with this equation, which is another famous equation. It's called the Sackur-Tetrode equation for the entropy of the ideal monatomic gas. Yeah, so again, you might have seen this. This is less famous than the ideal gas law, but this is also one of the well-known kind of equations in the study of gaseous systems. Okay, so again, you see the power of the statistical mechanics framework in giving us equations for the thermodynamic potentials using simple arguments and averaging operations and a little bit of math. The math is not too complicated, but you have to remember a couple of things here, including this approximation. Okay, let's talk about the chemical potential of the ideal gas, which can be calculated by this derivative. Again, same thing, substitute A for minus kT log Q, substitute Q for the ideal gas partition function, and with a little bit of math, again, I invoke Stirling's approximation. I end up with an equation that looks like this, and further simplifications can be done to end up with the final result, which is this. So what do I see here? The chemical potential can be expressed as Kb times T times log of all this thing, and you see this relation between chemical potential and the logarithm of the number of particles over here. Right, so now by using the ideal gas law, and you can, you are quite tempted to use it because you see we have number of particles here, we have volumes over there, we have some kBT terms, etc. So with, again, a little bit of manipulations, we end up with an important equation that gives us the chemical potential with respect to pressure. So you see that mu is equal to kBT times log of the pressure divided by kBT times all of this thing. But the point is that you have this relatively simple or interesting relation with respect to the pressure, which we will use later when we talk about adsorbates on the edge of a catalytic nanoparticle. And just to give you a bit of a preamble, using all that, we're going to, and the statistical mechanics framework, we're going to introduce or derive, right, prove the Langmuir isotherm using all of these arguments. Okay, so I think it's a good place to stop here because it's almost 3 o'clock. do we have any questions? And then the next time we're going to talk about the polyatomic, the diatomic ideal gas, and then these systems. Any questions? No, all good. If somebody's talking, you guys are all muted, so I cannot hear you. Okay, so I think, yeah, I think it's
I
all
don't have
good.
any questions.
Sounds good. Okay, so next time we're going to talk about the polyatomic and then in non-ideal adsorbates. We're probably going to skip this because it's a bit more complicated and we don't have that much time. If we have time in the end, because I also want to cover kinetic Monte Carlo, if we have time in the end after talking about kinetic Monte Carlo, we can go back to that. And of course, if you find this interesting for your research purposes, I'm happy to talk, individually. I realize that this is probably going to be useful for just very few of you. Okay, so I think that's the end of this session. Thanks again for attending, and
Yeah.
I'll see you next week.
Okay.